Alright, hopefully I got some of the noise the fan on my laptop was doing last time. I apologize for that. Going back to seeing those videos, there's this in the background, but it's been hot, and computers have to deal with that also. What we're going to do is we're going to continue looking at probability distributions. And we've had our binomial distribution where we have the probability of having X number of successful trials in a given number of trials. So we had N given trial, a number of trials, and X is how many are successful. And so we had NCX times the probability of success to the X times the probability of failure to the N minus X. This is the formula that underlies it. Now, the distributions themselves collect all the different variables of X, but it's not the only type of probability distributions we can have. And we're going to look at some other means of generating probabilities. And so what we're going to start with is we're going to look at the geometric. And we'll put this up here. This is binomial. And this is probably the most used, because you can turn almost anything into a success or failure, right? You have 5 different choices. Let's see, 1, 2, 3, 4. I'll make 6 different choices. 1, 2, 3, 4. Oh, I got my 5 in. And you want to know what, if you get this one, well, that becomes your success. Well, if you want to know getting 2, you take their total probability as the success. And so you can always look at the space you have and turn it into one thing or one probability. And it's going to be some of the tricks that we'll pull out. But binomial gets used a lot. But let's look at our geometric here. Let's define our geometric. And so the geometric is that it's, you repeat the trial. You repeat the trial until you get your first success. And so this measures how often you go until the value or until the success happens. Each trial is independent of each other. Right? Independence is the key here. Right? None of these influence or update the probabilities of the other ones. We go back to our definitions of probability. Independent probability events do not change your sample space or your possible outcomes. So in doing such, the probability ends up being the same. And so that's the third rule here. The probability is constant for each trial. And so in our geometric, we have a constant probability. And so our random variable X is the number of the first success. And so this has a distribution for when the probability of the first success is going to be P times X is equal to P, because we're only going to have one success. And then in Q times X minus 1. And so this is our geometric. But notice something weird here. Geometric is related to our binomial. Right? We're looking for only one output, which is one success, but we don't know how many failures are in front. And we're going to work on where that comes from and what it does with the geometric. But so for a geometric, let's go here and we're going to say that, let's see, again, using the examples from the book and the slides, and I'll make sure that we use those with our technology as we come through. So we study cell phones. I don't study cell phones, but someone studies cell phones. And they find that manufacturer A has a failure rate. So the chance of failure is 43%. Okay. Manufacturer A's, their failure rate is 43%. We're going to grab 4 smartphones from manufacturer A. So we're going to grab at 1, 2, 3, 4. And so we check the first one, it's good. Second one's good. Third one's good. and the fourth one's going to be our failure. So we want to know the probability of grabbing these four things. What's the chance that the fourth one fails? And these type of things are useful because if you're running something that has consumables that have a failure percentage, you might want to put a tolerance level, right? So if you're using something consumable and you know that you should have a failure that goes below your tolerance percentage, what probability you don't want to accept at a certain number, then you put a threshold before that number, making sure that you can deal with the failure. And that's the reason we look at these things. But so in this, our success is the failure. Isn't that weird? Our success is the failure, right? Well, our experiment is going to yield a result when a phone fails. So I'll put 0.43. And that means that our Q variable is going to be 1 minus 0.43 because it's the complementary space to that. And so that's going to be 0.57. And then we're going to say we want the first failure, or the success of our experiment, on the fourth phone. And so the probability in a geometric distribution of the fourth phone being a failure is going to be 0.43 times 0.57 to the third power. Now notice this has the same kind of thing going on with the exponents that you had with the binomial, though. And let me scroll up and see the binomial here. So we can say the exponents with the binomial, and I pointed this out before, if you add x and n minus x, you get the total number of trials. In the geometric, if you add the exponent here, well, we don't write ones in mathematics. Every number is to the first power, and so this gives me a total of 4 on the fourth trial. And so it has some similar accounting practices that you can make sure that you're putting the right things into place. But running over to a calculator, this ends up being about, we'll round here, 8%. It's like 0.07963. And so this is what a geometric distribution looks like. It's how far can you go until the first thing gives you a success. All right, another probability of distribution that's used fairly often, and it's going to be one of the last of our discrete probability distributions. We're going to want to look at continuous probability distributions after that. Is going to be the Poisson distribution, named after the person who kind of championed it. And so it's a discrete probability distribution where the experiment is counting the number of things that occur, in an interval. So if I say that I have, I'll even say, and it's the probability that the same event occurs in each interval. For this to work, that number is independent. And so I guess really the key hang up here for each interval is, what do we mean by an interval? And so an interval is anything that covers a range of values. So for example, within a day, right, there's 24 hours within a day, right? Around the clock twice. I can say that on average, people use the bathroom twice, right? 2 times in 24 hours. I actually think the average is a little lower than that, but it's a different story. Or higher than that, I'm just making up a number. And so this average in a given interval, this is the count, the number of times something happens, This is the interval. And so on any given day, that's the number that we're looking for. Now, this has one of the weirdest looking mathematical formulas for us right now. And how this is going to work is how we want to put this together. And so I'm just going to do the formula and then we're going to use it a couple times. And then in my Excel slide, I'll explain Excel has functions built in to do these mathematics for us. I hope we are moving over to using your computer to do your calculations for you instead of a calculator. And I will say this every time people are struggling with computer stuff. It's like, I know, but I've never seen anyone use a calculator in work unless it's just an adding machine. And even then, now people are putting things into Excel and using the sum. And for the type of math you want to do, you want your, if this were your job, you want your computer to be doing the work for you. Let's get that hurdle out of the way now. Doesn't mean the formulas don't have value. There are language for discussing these things. And so the probability that a certain number of things will happen, given that the average is this bit, to the power of the number of things I want. And then I'm going to take a special number, it's like pi, but it's called e, to the power of the average, the mean, divided by the factorial of the number of times you're looking at for. Now, e is a special number. It's 1 plus 1 over n to the nth as n goes to infinity. And that creates this number that's approximately 2.71818. It's actually, the number pops up in a lot of mathematics because this idea of adding a smaller bit and a smaller bit and a smaller bit to things is a very useful tool. And this was actually one of the few mathematical terms was discovered in banking as a way of doing continual interest. Go figure. So let's look at using this, and then we'll bring our technology to help us get this. So if there were at a particular intersection, and there's my interval. The interval has now become both time and space. And so at this one intersection, in 1 month, there are 3 accidents. Something about its design, right? You're working in an engineering firm. Let me come up here. I'll clear this out. For some reason I have a smaller thing today, but so there are 3 accidents per month at a given intersection. So we have our interval in time and the number of things. And so we want to know what is the probability in a certain month that there will be 4. And so we're going to take our Poisson distribution, mu to the x, e to the negative mu over x factorial, and we're going to say what's the probability that there are 4 in a month. And so we take 3 to the 4th e to the negative 3 over 4 factorial. And calculators have an e button. It's usually around the natural log key. But we'll plug this into the calculator here, and we get 0.168031, so on. And so it's about a 16% chance, which is not a bad idea. It's not too far away from the mean. So we would expect the further we get away from the mean, the larger this number would be. And let me see, I think that's the last example I'm going to do until we use technology. And these are our last 2 distributions. The thing to look for with these distributions is how they appear. I mean, the number of things in a given set of space. I think there's a problem that'll talk about the number of wildlife that appear within 1 acre. And then so if you go randomly and you pick one other acre, what's the chances that you see 7, right? Like the average over here is you see 3 deer every evening. What's the chance you go over to this acre over here and you see 7? And if the percentages should be the same through all of these, the probability should be the same. The Poisson distribution will give it to us, as we have the number of things in a given interval, which happens to be an acre of land. And so that interval can be time, or it can be space. And there are other intervals that will pop up with this. So I'm going to end this lecture here, I'll pop it up, and then we're going to look at probably the biggest distribution, which is when we get into our continuous distributions, which is our Gaussian or the standard normal.